Welcome to AP Chemistry. We now turn to merge our understanding of equilibrium with the thermodynamic notion of spontaneity. According to the principle of microscopic reversibility, all elementary reactions are reversible. An interesting implication of this is our notion of time. Time, in a certain sense, does not exist at the microscopic scale when the system is at equilibrium. For if we were to take a video of collisions of our particles, we would not be able to tell if it was playing in the forward or reverse direction at equilibrium. There is no priority in the direction of the collisions, and since in an equilibrial system there is only a forward step collision and a reverse step collision, there would appear no difference with respect to time. The tape could be played in forward and reverse directions, and it would still appear as if time was proceeding in the same direction. This leads us to inquire as to the nature of irreversibility in reference to chemical systems. Equilibrial systems are a unique case of really reversible processes in which change in G, the measure of our free energy loss, is relatively small in comparison to the activation energy of the forward process. Or put alternatively, the activation energy of the forward reaction in reference to the reverse process is very similar. This situation is unique only to equilibrial systems. The reason why all reactions do not proceed in this fashion is because of a larger difference between change in G and the activation energy of the forward process. The equilibrium point is thus the lowest point of free energy in our system, and the equilibrium system progresses spontaneously to this point. If the equilibrium system is disturbed in some way, in effect, free energy being added to the system will naturally adjust its position so that it again reaches the lowest point in free energy. With this in mind, we must distinguish between standard free energy change and non-standard free energy change. Based upon a difference in pressure or concentration and temperature, we will need to add or subtract free energy from the calculated standard free energy value in order to portray the system accurately. With this simple equation, that G non-standard is equal to G at standard conditions plus RT natural log of pressure, we can substitute in for each component of our chemical system as shown above and simplify as seen in the equations below. After we simplify, we are provided with an equation that generally applies to any chemical system. The change in free energy not at standard conditions is equal to the change in free energy at standard conditions plus RT natural log of Q. The point here is that we can now calculate exactly the spontaneity of any equilibrium system when it is not at standard conditions. Just like change in G at standard conditions was intimately connected to K, the equilibrium constant, so also change in G at non-standard conditions is intimately connected to Q, the reaction quotient. We can also rearrange our last equation so that we can solve for K for any chemical system if we have a standard value for change in G. These two equations and the tables provided are the most important takeaways from this unit. The point of non-standard change in G calculations is to determine the maximum possible useful work obtainable from a chemical process. But the truth is, achieving this maximum work available from a spontaneous process is only hypothetical. All real processes that we attempt to utilize, say for instance in the redox chemical process of a car battery, will always waste energy due to heat loss and entropic generation. The universe is always more different after such a cyclical process has been performed. And in this respect, the process in its entirety is irreversible. Till next time we consider the mysteries of the absolute, Crip.